check out this little square wave triangle wave generator. Wouldn't it be cool if there was a way we could modify this to produce sawtooth waves? And wouldn't it be even more cool if we could adjust the symmetry on those sawtooth waves? I'm Professor Fiore, and I'm going to explain to you exactly how to do that right now. All right, let's dive into this. What we're going to look at is a little circuit, not too complicated as it turns out, that can produce triangle waves, square waves, and sawtooth waves, and you get to control, you could either call it the duty cycle of the square pulse or the symmetry of the sawtooth. What are we talking about? The basic configuration is a 2 op-amp comparator integrator. And this is explained in great detail in my op-amp book, which you can download for free. And what we're going to do is start with that, and then I'm going to show you how we're going to alter it to get into these sawtooth waves and what we have to do for the symmetry control and so forth. The resulting circuit has about a 20-to-1 range, assuming you're not doing any kind of range switching. In other words, using like a rotary switch and capacitors to change like that. Just rotate one pot, right? That should be a sufficient amount for most applications. The range of frequencies this will work over will vary from infrasonics, so you could use this as an LFO, right? Low frequency oscillator, well into the audio range, right? I mean, this is not designed for like microwave or anything like that, or radio frequencies, but through that range, right? Fractional hertz up to tens of kilohertz, basically. The circuit uses common off-the-shelf parts. So in its nicest sort of configuration, it uses 3 op-amps and you know, a handful of pots, some resistors, capacitor. You can add to it, you know, all depending on what really you need to get out of it. But, you know, the cool thing is that you have a single potentiometer that you can rotate. And it'll go from one extreme. You'll have a sawtooth with a slow rise and a fast fall. You keep rotating, it'll turn into a nice triangle wave, you know, 50-50 rise fall. And then you keep rotating again, and you get the exact opposite. In other words, now you'll have a fast rise and a slow fall. Okay? Frequency will stay the same as you're doing that. Now, there are simple circuits you can create where you can adjust the symmetry, but when you do it, yeah, the symmetry changes, but the frequency also changes. So this circuit, you dial in a frequency, and then you would dial in your symmetry, all right? Completely separate, all right? So you have 2 simultaneous outputs, a square wave output and a triangle sawtooth combo output. The level on the square wave is fixed. The triangle wave, you can program to certain levels, but if you really need a lot of adjustability on that, you would probably want to add maybe a potentiometer followed by a buffer or maybe a small gain stage, depending on how big you want the output to be. All right. It is possible to reduce this to just 2 op-amps if you don't mind some inaccuracy in the tracking with the control pot, which I'll explain momentarily. First, let's take a look at the circuit this is all built on. So this is a basic comparator with hysteresis driving an integrator. And here's the way it works very quickly. Like I said, I have covered this in the free op-amp textbook in greater detail. I'm just going to give you a real quick overview. And there is a separate video just on this. If you want to check that out, it's you know, in that section of the op-amp playlist where we talk about oscillators. So it's, you know, right next to this, next door neighbors. But in any case, let's just say you turn this on and this output is high, right? Like I said, this is essentially a comparator. So let's say this is high. We're using 9-volt power supplies on this particular one. So this is going to saturate, you know, 7.5 volts, maybe something like that, whatever. So we get a voltage out here, and the pin 2 of the second op-amp as an integrator, this is a virtual ground. So all of that voltage drops across R9, and that creates an input current. And because the input current into the op amp is negligible, all of that current flows through C2, and that produces a drop across this, plus on this side to minus. Of course, this side is the virtual ground, which means that the output is actually negative. So as this current pumps through here, we get a nice linear change in the current, right? In this case, it's diving down. Nice straight line, because this is a constant current source, right? Fixed voltage, fixed resistance, and boom, we get a constant current source. So that voltage is then fed back over here into this first op amp, which, like I said, is a comparator. And essentially what happens is there's a voltage divider between this 22K R8 and this 10K R7. And the point is, the more negative this voltage over here becomes, we're going to start seeing this voltage right here on pin 3 going negative, 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 more and more negative, because basically this is just dividing out between whatever this output is, which currently is positive saturation, right, and whatever this output is, which, as we said, depends on how far along in the charge cycle we are with C2, right? But this thing is just going down, 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 down. Eventually, if we wait long enough, this voltage will get so negative that it will pull this node below ground, right? So your other pin on this op amp is set to ground. So when that happens, the inverting input is more positive than the non-inverting input. And that flips the polarity of the differential input, which means it flips the polarity of the output. So now, instead of being positive saturation, this thing goes to negative saturation. And now we're going to sink current. Current is not going to go this way through R9, this 10K. And that pulls the current through C2 in this direction, the opposite direction. So, right, this cap voltage was going down, 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 referencing the output of op amp number 2. And now it's going to go up, 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 up. And eventually, that's going to get high enough, again, fed back here, that this point is going to go positive with respect to pin 2. And bink, this output goes positive again. And then what happens? Current goes this way, the cap starts to discharge, and off we go, right? And this just keeps on going, keeps on going, keeps on going. So we can determine exactly what that frequency is based on the RC time constant over here and what we set up for the thresholds between these two resistors, right? R8 and R7, as they're labeled here. But let's just run a transient analysis, and you can see what we're looking at. Okay, so here's the square wave coming out, right? And here's our triangle wave. Notice how nice and straight the edges are on this. So I'm going to grab a little cursor over here. First, just check the level, right? We can see, like I said, it's going to be maybe a couple of diode drops below the power supplies. So we're getting like 7.4, right? That makes good sense. So here we are at this point, right, on this edge. Here we are positive. And what's happening? Well, as I said initially, the current's going to be going in this direction. So the voltage across the cap, right, was going to be plus to minus like this, which means the output on this op amp is negative. Here, I'll move this over just a smidge so you can see it. Right, so this is going negative as this current pumps in. And that's exactly what we see, right? Here's the triangle output, which is right here, going negative, 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 negative. It gets negative enough, and at this point, that's when the signal is fed back, and we flip the polarity on the input, and you can see, right, we come to this instant, and now the first op amp goes negative, and now we see the cap starting to charge, right? And it just keeps doing this process over and over and over and over again. All right. So that's the basic, starting point of our circuit. There's no convenient way in this circuit to, create a sawtooth. To create a sawtooth, we would actually need to change the charge and discharge times, in other words, the currents that are feeding the capacitor, between the positive and negative cycles. Right? In other words, on the charge up versus the discharge down, or charge down, however you want to call it, because either way it's active, right? You would have to be able to change those to get some kind of sawtooth out of here. Well, you can do that. Bingo. I'll explain this in just a moment. But first, before I do, I want you to right now ignore this stuff right in here. This is really here for like accuracy and something we're going to get to in just a sec. So just ignore this pot, these Schottky diodes, and this little op-amp buffer. This is only a high input impedance, low output impedance, voltage gain of 1. Just ignore this. Just pretend that this point right here is going directly to R3. All right? And that's almost what we had in the preceding circuit, except that instead of having a single resistor driving this cap, we have a somewhat more complicated circuit with that resistor, a couple of rheostats, and a couple of Schottky diodes. So, why am I using Schottky diodes here instead of just regular signal diodes? Well, 2 reasons. A, they're fast, which is good, but a major reason is because the voltage drop across them in forward bias is smaller. So instead of getting 7/10, maybe we're only going to get 3/10 or 4/10, and that's going to improve, as you'll see momentarily, the range and accuracy of this particular circuit, right? But still, we're just going to think of these as kind of like switches, allowing current in this direction here, allowing current in the direction like this for the upper path, right? So here's what happens. Output goes high. Again, just pretend it's over here. And that voltage, again, here is your virtual ground. That voltage drops across this network. So it's positive right now, right? So I've got R1. Notice SD3, this Schottky diode is reverse biased, so you can just ignore this upper path. All we have is this lower resistor, rheostat basically, and this. So that voltage drops across this combo. Subtract off the Schottky potential. So, we had, I think, 7.4, something like that, volts out of here. So you should drop that off. So now it's going to be like 7 volts. But that 7 volts drops across this resistor and this rheostat. So depending on where the rheostat is set, that will set the current. And that current is what's going to go through C1 to create, again, that charge rate. And that voltage, again, gets set back here into the little comparator with hysteresis. And, we're back to where we were in the explanation a moment ago. But the interesting thing happens when this flips state, because now this output goes negative. Now we have a negative voltage across this. And guess what? SD4 is now reverse biased. So when it pulls current, it's going to pull it through the upper channel, let's call it, right? The upper path. And this is set at a different resistance value, which means that this current is different than the current we had for a positive input. And of course, the current gets pulled through C1, different current. There's going to be a different slope on the voltage change here, which means different slope on the triangle wave, right? This triangle wave output gets fed back and off we go. So this thing's going to flip back and forth, all right? Positive, one path, negative, the other path. Now here's the cool part about this. We take 2 identical potentiometers. We actually go out and we buy a dual gang pot, right? So 2 pots on 1 common shaft. But we're going to wire them as rheostats and we're going to reverse wire them. In other words, if you were looking at the back of this, right, there would be 3 terminals. You have a left terminal, a center terminal, and the right terminal. So the center terminal is going to be the wiper arm. And I'm just going to say that's your left terminal. This is your right terminal. In one case, we're going to use the left terminal and the center terminal. In the other case, we're going to use the center terminal and the right terminal. What? Okay, see, notice this little thing. I know it's wired kind of symmetrically, but notice I've like flipped the pot, right? This little circle over here represents the bottom of the pot. In other words, it would represent like the left side, right? Or the right side, depending on whether you're looking at the front or the back. That's the important thing, right? You use the opposite. So what does that mean? Well, if I turn this to the middle, right, this is going to be 50-50. In other words, this is going to have 50K and this is going to have 50K. If I crank it to one extreme, it's essentially 0 and 100. In other words, let's say this one is going to be 0 ohms and this is going to be 100%. This is going to be 100K. And then when you crank it the other way, it's going to be the exact opposite. This will be the 0 and this will be the 100K. So the symmetry is actually adjustable between the 1K and the 100K. It's 100 to 1. So you can get a really nice sawtooth out of this. All right. So that's how we do the sawtooth, right? P3, P2, this combo does the sawtooth. Now, we have to look at the frequency control of this whole thing, right? Because I want adjustable frequency on this. You might think, well, I'll just turn R3 into a rheostat. That's not going to work. Because what will end up happening is, depending on the size of R3 and the setting you have for these pots, it's going to affect what the symmetry adjustment range is. So, if I threw a 100K pot in here and I set it up as a rheostat, well, when I bring it down to a low value, like 1 or 2K, everything works as I just said. But if I crank this up, because I want to, again, change the frequency, if I bring this up to like 50K, well, then, the biggest change I can have is between a 50 and 100, right? That's only a 2 to 1. So, not so great, All right, what else can we do? Well, instead of attacking the resistance, remember, it's the current charging and discharging C1 that really matters here. So what I can do is change the voltage that feeds this whole thing. That's what this pot does, right? So this is saturation. And now we control a percentage of that, which is going to drop out here. Now, I have included this second pair of Schottky diodes to sort of compensate for these. Because, you have to have a voltage over here that's at least enough to turn on the Schottky diode. And so let's say it's 0.4 volts. Well, what if you dial up, 0.3 volts over here? Nothing happens. The circuit's not going to oscillate because you never have enough current to turn this on and charge the cap. So by putting this in, they kind of cancel each other out, right? Because you're never going to have a voltage off this wiper arm that's smaller than the turn on of one of these Schottky diodes. And that's what you have over here. So you can kind of like just, in a way, kind of ignore that they even exist, right? We have to have them here in order to sort of direct the path of current flow. But here we have them just to sort of compensate for the unideal effect. If somebody ever invents a diode that has like a 1 millivolt turn on, oh man, life would be great. But I ain't holding my breath for that. In any case, so, we just adjust this pot, which adjusts this voltage, which in turn adjusts the current. Why is there an op amp here? Why is there a buffer here? Because depending on where this is set, where this pot over here is set, the size of this resistor and the size of the pot, there's an interaction. So let's say you crank this to an extreme so that, one of these is shorted and the other is at 100K. So when this is, at 0, then you only have 1K total. And that winds up being, if you don't have the buffer, that winds up being in parallel with this pot, or part of the pot as you've adjusted this. And that loads the pot. And the end result is the actual voltage that you get out here is going to vary. It'll be different. And that's going to mess with the frequency and the symmetry of this output waveform. If that's not a big deal, in other words, if you're just going to like set this by ear, like let's say it's going to be used for an LFO, you could just deep six this. But if you want to, keep things nice and consistent, like more like a laboratory kind of thing, or maybe you're going to, etch appropriate values, on the front panel of this for the pots, you're going to need consistency. Well, you're going to want to put you're going to want to put that buffer in there. And it's not a big deal. It's just one op amp. There's, it's set up as a buffer, so you don't even need resistors. It's just the one op amp and a wire, right? No biggie. Your other option to prevent the loading would be to make this pot really tiny. Even at 1K, there's going to be a noticeable loading. I mean, if you brought this down to 100 ohms, the loading would be minimal, but now you got a 100 ohm load for this op amp over here. So this is going to run out of juice really quick. Current limit. Okay, so that's not such a good idea. If you brought it up to like, let's say a 1K, which is kind of pushing it, then you'd have to increase all these things. And, now you're looking at mega ohm or larger pots over here. And, now offsets and drift and noise and whatever gets worse. So this seems to be a nice compromise for all of that. Like I said, it's just a simple op amp. And you'd use the same kind of op amp. You still want the speed out here to keep your square wave coming out. Pretty nice. This would be the full amplitude square. You know, you theoretically could tap out here, but I wouldn't recommend it because this is isolated with the buffer. All right. Okay. Let's take a look at some output waveforms. So, before I do that, let me just double check the settings. Okay, so we're at 30%. So this is going to be kind of a middle of the road setting as far as frequency is concerned. And I've got, let's see, 5%. So you're going to set both of these because I flipped one of them. You're going to set them both to the same value, right? The setting on this is 5% each. So this is going to produce a sawtooth that's pretty dramatic, right? The difference between the rise slope and the fall slope is going to be very obvious. And there we go. All right. Bring this out so we can see it a little better. All right, so here's the square wave output. You see those little pulses. And, you know, as expected, the duty cycle on here is changing right along with the symmetry on the triangle. As a matter of fact, we can zoom in on this a little bit. All right, so you can see that we're getting some, I'm not convinced that that's real. That might just be a simulation artifact. I'm not 100% sure. But in any case, you know, you can see, right? Here's your rise, there's your fall, there's your rise, there's your fall. Clearly sawtooth, right? So let's go and kind of go the other way. Let's make it like 90-90. I'm just pulling 90 out of the air here. So now the slope is going to be in the opposite sort of way. Well, you know, as long as we're doing it, well, okay, yeah, I'll do the frequency separately. All right, so let's kind of zoom in on this as well. All right, this is a nicer looking one. So you can see a nice fat piece up here, right? Instead of what we had before, right? The preceding one, very skinny on top. So small duty cycle, slow rise on the triangle, big fat duty cycle, right? Quick rise, and then slow fall, right? So you look at that green on the bottom, you can see the obvious change here. Okay, beauty. Now, what about a frequency change? Okay, so let's bring this back. All right, there's our base, and then we can change the setting on this. So if I bring this down to like 10%, I have a smaller voltage here, so the current driving it should be smaller. Should take longer. All right, and that's what we're seeing, right? Lower frequency. Okay, now if we go the other way, you know, let's just crank this up to 90%. Do it again. Wah, 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 wah. Oh, clearly a much higher frequency, right? So this was like 30% or something like that, and then we got down to like 10, and you know, now we're way up, right? So yeah, this will work. If you measure this out, which I already have, you're going to get like a good 20-to-1 ratio. Okay, so, and again, you can see what the amplitudes are here for the triangle, right? So this is, like I said, just a little bit less than a power supply, maybe 2 diode drops, good estimate for saturation. And you know, this is basically set by, that amplitude is basically set by the R1, R2 ratio. Again, explained all in detail in the book. All right, so you can see, yeah, we're getting some pretty good results here, right? You look at these changes. But, you know, look at the amplitudes, right? Those are all on this, on the triangle, or sawtooth, excuse me, right? They're all right around the same value. You think, you know, the only one we didn't do actually was an actual triangle wave, right? So let's just do that. Put 50 in there. You know, let's be complete about the whole thing. 50. And, you know, I'm going to want to see the waveform pretty well. So let's slow it down a little bit. Let's go down to 10% there. And transient, off we go. All right. That looks like a pretty nice triangle wave. Maybe we could zoom in on it a little bit. All right. Nice straight sides, nice symmetry. Oh, it's gorgeous. How can you not love that? All right. Okay, so pretty cool circuit, I think, right? You got a triangle wave and a sawtooth wave out of the same output. And you can control that sort of morphing between the two sawtooth extremes in the triangle. Put the knob in the middle and you get a triangle. You go to the extremes and you get, the various sawtooth shapes. And then you have a separate output for the square wave. They're locked together in frequency, all right? And you get a completely separate control there for the frequency. And you got a 20-to-1 range. Wow, how can you complain? All right. And notice I ran this on 9 volts for those of you that want to make a little portable generator, right? So you could use this as an audio generator, with 318s. That would be no sweat making a decent audio generator, but it will go down to really low frequencies, infrasonics. So, if you want to use this as a low frequency oscillator, as an LFO for, some kind of special effect or synthesis or something like that, you could do that too. All right. Well, I hope you've enjoyed this. And this is Professor Fiore saying, take care. Have a good one.